So a few weeks ago, Google released their Gemma series of models. These are open models that are based on their Gemini research and training methodologies that come in the 2 billion and 7 billion range. And Google has released them on Hugging Face, so anyone can download, retrain, and upload them as they see fit. So I thought I would go ahead and show how to get started with these models using the Hugging Face libraries, how to pull them down from Hugging Face, how to call inference on them, and how to get started just kind of playing around with them so you can build your own apps with them. So first stop in this journey is we need to actually get permission to download the models onto our environment. So to do that, we first need to go to Hugging Face, and we just need to go to the search bar here and look up the models we want. So in this case, we're looking for the Google Gemma models. Now, as I mentioned before, they do come in 2 billion and 7 billion in range, but they do have two variants. There's the regular pre-trained version, and then there's the instruction tuned version, which you can see right here by the IT. Now, the base models just have continuation type prompts, meaning that whenever you feed it information, it's just going to try and continue with that information, whatever it thinks would come next. It's not really tuned to follow instructions or to chat, and that's where the instruction tune model comes in. They've actually been fine-tuned a little bit to act more as chatbots whenever they see a certain prompt style, and this is what I would recommend you getting started with whenever you're starting to experiment with these models. They're just a little bit more usable, and they apply a little bit more directly to most use cases. So this is the model that we're going to use for this example. When you first come to this page, you're actually going to be greeted down here with a terms of service. I have already accepted these terms of services. I've already played around with these models a little bit, but you are going to have to accept these in order to download the models from Hugging Face. Now, the terms of service are pretty easy to understand, and they're actually pretty flexible. Like, you can use these models for commercial apps, you can use them however you want, you can retrain them, you can redistribute the retrained versions of it. As long as you don't do evil stuff, that's mostly it. Like, as long as you're not actively making the world a worse place with these models, Google is okay with you doing whatever you want to do. So you just need to accept the terms of service, and then you're allowed to log into Hugging Face and actually download the models in your environment. In order to do that, you're going to need an access token. To find that, you just come up here to the right and you go to your profile. Then you go to profile settings, and you want to go to access tokens. Now, if this is your first time here on Hugging Face, you just have to create a new token. You can create a read-only token, meaning you can pull any of the models down. But if you have any interest in actually posting trained models, go ahead and create a write token. This allows you to not only pull models, but also write your own back to Hugging Face. So the first time you come here, you just need to create a new token. And whenever you do that, you just need to copy the token over here. And just hold on to this for a minute because we're going to be using this in our environment to prove that we have accepted the terms of service and we are who we say we are. So that's everything we need to do in the Hugging Face corner of the world. Let's go ahead and hop over to our environment. So for my environment, I decided to go ahead and use Google Colab. This is a really good environment if you don't have a GPU on your own system, and it actually comes with some pretty high power GPUs if you spend a little bit of money and get the Pro version. So I am using an A100 GPU that has 40 gigabytes of memory, which is more than enough to fit our 7 billion Gemma model. But obviously, if you have your own environment with your own GPU, you can use that as well. So the first thing that we're going to want to do is we're going to want to install the libraries that we need from Hugging Face. So if we do pip install, and we're going to do upgrade just in case that we have these packages pre-installed on the system. And we're going to need the transformers library, and we're going to need the accelerate library. Now, both of these packages are from Hugging Face, and they're going to help us pull the model down from their hub, and it'll also help us load it into our GPU using the accelerate library. Now, another package that you are going to need that already comes pre-installed in Google Colab is the PyTorch module, and that's because Hugging Face loads all the models into a PyTorch model by default. So we can actually use PyTorch to define data types if we want to change that around. If we want to do any fine-tuning, we can go ahead and use PyTorch based methods. So it's helpful to go ahead and have that library installed, especially if you want to get deep down into the model and actually mess around with it and not just do inference. But as I mentioned before, Google Colab already has that installed, so we don't need to worry about it. So let's go ahead and run this and install the libraries. The next thing we need to do is we need to embed our access token into our environment. That way, whenever we actually go to the hub and actually try and pull down the model ourselves, Hugging Face knows who we are and knows that we have permission to actually use these models. So if you're in a notebook environment, there's an easy way to do this. So if you just do from Hugging Face hub import notebook login and go ahead and call this function, This is actually going to embed an HTML widget into your notebook that you can go ahead and just copy and paste your token into. And just like that, so you can go ahead and copy your token that you got from Hugging Face and go ahead and log it. So now we have our token embedded into our environment. Anytime we go to the hub, it's going to know who we are. And since these are gated models, we're going to need that to actually pull down the Gemma models. So now we can go ahead and start loading the model into our environment. So to get started, we need to go ahead and import some libraries. So first we're going to import Torch, and then we're going to import from our transformers library, if I can spell it. We're going to need the auto tokenizer, the auto model for causal LM, and we're going to need set seed. Now, it's a good habit to get into to go ahead and manually set the seed when you are able to do so, just so you can reproduce results later on. Now we're going to define the model that we want. So we're going to do model checkpoint, and we're looking for the Google Gemma 7 billion, and we want the instruction tuned version. Now we're going to load in the tokenizer. Auto tokenizer dot from retrained, and we're going to pass in the model checkpoint. So if this is the first time that you're using a local LLM and you're just kind of getting started with this, you're not quite sure what a tokenizer does. The basic gist of it is the tokenizer takes in raw English text and it converts them into tokens, which are just numbers that the LLM can understand and then use in its calculations to predict what the next token it should output is. So for example, if we have the input I am recording and we pass this through the tokenizer, it might chop this up into an I token, an am token, a record token, and an ing token. So an important thing to note is that it's not a one-for-one. So there's not one token per word. It breaks it down a little bit finer than that because this recording really is two concepts. One is the concept of recording something, as in like storing something to view later, and the idea of the ing part, meaning that you are actively doing it. And so tokenizing breaks this down into bite-sized information that the LLM can then understand, that it can use to then punch into, that it can then use to do its calculations. So this auto tokenizer is going to go out to our model checkpoint. It's going to see what sort of tokenizer that it needs to pull for this model, and it's going to go ahead and load all of it for us so we don't have to manually specify which one we want. So now that we have the tokenizer, it's actually time to load the model itself. So we're going to do model is equal to auto model for causal LM dot from retrained, and we're going to pass in our model checkpoint. And we're also going to pass in a device map, and we're going to specify CUDA. So what this is doing is it's saying, okay, we don't want the model to be loaded onto the CPU, which is how it typically loads it by default. We want you to place this model on a specific device, which we're identifying as CUDA. So this is basically saying, look, there's a GPU on this machine. It's going to be under the name CUDA because that's the runtime environment that GPUs typically run on. And we want you to load that model into that device. Now, another value that you can specify here is the torch D type or the torch data type. Now, by default, the model is going to be loaded as a 32-bit float number. And whenever you load it onto the GPU, it's going to take up just over 32 gigabytes of memory. Now, for a lot of GPUs, this is way too much. For the A100, it has 40 gigabytes, so it'll be able to fit comfortably on there. But if you're on a slightly smaller GPU, like a 4090 or something like that, then you really don't have 32 gigabytes to actually use. So to help with that, you can actually specify the data type that it wants to load the model into, and it will actually convert it into that data type whenever it's loading it in. So a good one that I found is torch bfloat 16, and this stands for brain float 16. This is a newer data type that was made to kind of help with LLM processing, and it's actually really good. So whenever you go from 32 to 16, you're not losing too much accuracy. So this is a really good alternative, and it will actually bring the memory requirements down from 32 to just over 16. Now, it's important to note for Google Colab users, 16 gigabytes is still too much for a V100. It caps out at 16, and this model is actually slightly over 16 gigabytes. So it's still a little bit too large for a V100 GPU. But if you have something like a 3090 or 4090, then this will make it so that you can actually load this model without any further quantization. Now, I am planning to do a full video on quantization and how you can actually make this model a lot smaller to fit on smaller GPUs, or just free up memory so that you can do your own training on these models, but that's a subject for another time and requires its own sort of video to kind of go over all that. But for this video, since I have 40 gigabytes, I'm going to use 40 gigabytes, so I'm going to load this in on the full 32-bit floating point numbers that it was originally trained for. So now that we have all that specified, let's go ahead and run this code. Now, if this is your first time running your code in this environment, it's going to take a while to actually load in the tokenizer and the model. So sit back and relax and just wait for it to finish. All right, the model is loaded. So let's go ahead and do a little bit of exploring here. So we're going to print out the schematics for this model. So all the details about the different layer types. And we're going to print out the model D type, just as a sanity check to make sure it loaded in as the proper data type that we were expecting. So this first little bit here are all the different layers and the names of the model. So you can see here that we have the attention layer, we have the multi-layer perceptron layer, we have normalization layers, and then we have a final output layer down here. So if you're going to be training your model, it's good to familiarize yourself with what layers are in the model and what their names are, because that's going to be very important if you're doing things like Q LoRa. You want to know what these are named so that you can go and find them later so you can make your adjustments on them. And the final thing is that this is loaded in as a float 32, which is what we expected. All right, so let's go ahead and start feeding this model some text that it can predict on. So let's start off with a prompt, and this is going to be a completion prompt, so we're not going to add any sort of conversation prompt to it just yet. We'll do that in just a moment. We just want to make sure that this model is working and that it can output text as it is. So let's start with just a simple prompt here. And leave it kind of open-ended. I'm kind of curious to see what this LLM is going to think the reason for Dr. Pepper being the best soda actually is. So now that we have our prompt, it's time to turn this into tokens. So we're going to do token inputs. We're going to pass this into our tokenizer that we made before, specify our prompt, and we're going to ask it to return it as a tensor. There we go. And we're going to say, go ahead and send this to the GPU as well. So this return tensors is basically telling us how it should return these tokens to us. We're basically telling it to return it as a PyTorch tensor, meaning that it is already ready to go into our model without any further processing. And this 2CUDA is telling it to load it onto the GPU where our model is so that we can feed it directly into it. So let's go ahead and do a little bit more investigating and actually print out this token inputs just so you can see what it actually returns and what the model is going to see when we feed it into it. And the output of the tokenizer, as you can see here, is a dictionary object with two values. One is the input IDs and the other is the attention mask. But all we really need to focus on is the input IDs because this is going to be the input into our model. And you can see here that the actual value of the tensor are the token IDs for the text that we inputted. So our model are going to see these IDs. It's going to understand what word or part of a word that it's looking at, and it's going to use that to understand the input and produce some output for us. So let's go ahead and feed this into our model and actually get some output. So we're going to do some token outputs. We're going to do model.generate. And we're going to pass in our input IDs from our token inputs that we got back from the tokenizer. Next up, we're going to define the max number of tokens. And we're going to just put in an arbitrary number right here. This way, the LLM doesn't get into a loop. For the Gemma models, I don't think this is a big issue, but depending on what models you're actually using from Hugging Face, you may want to specify just so that it ends in a timely manner and it doesn't kind of get into a loop or ramble on. Now, these are all the things we need to actually get output from the model, but I'm going to add two more values to this call, which is doSample. And we're going to define that as true. And we're going to pass in a temperature. Now, what both of these values are going to do is it's going to make the output for the model non-deterministic. So the default way that this model is going to run is it's going to output a huge tensor that is the probability of each word in its corpus and how likely it is to follow this piece of text. So basically, it's trying to predict what word is going to come next in our prompt up here. And the default method of running this is to just select the highest probable word and say that that is the next word. And for some use cases, this works perfectly fine. But if you have a more open-ended type question like our prompt here, which is a little bit more open-ended and allows for more creativity, you may want the model to allow it to select words that are slightly less likely, but still kind of like. And that's what this temperature and do sample are doing. So what's do sample is telling this call is to say, okay, we don't want you to take just the most likely word, but we want you to kind of sample across all words and pick from the most likely ones from that based on some random distribution. And this temperature is defining how more likely a word is to be selected. So you can kind of think about it this way. If the temperature is really, really high, that means that it's more likely to output absolute gibberish. If the temperature is really, really low, then that means that the model is going to select the most likely words. So I have the temperature set to 0 0.5, which is actually probably higher than it should be, but I'm kind of curious to see what it's just going to output from here and whether or not it's going to be even legible at all. But typically you want a little bit of randomness to the output, just so that way the LLM doesn't sound quite so robotic. It can deliver the same sort of answer in a little bit different ways, which makes it feel a little bit more conversational. But whether or not you need sampling and what the temperature should be whenever you do sample is really up to you and your use case. So with that call done, we are now getting the output for our model from our prompt. Now we need to actually decode it back into the English language so we can actually see what the model thinks the answer to this prompt actually is. So if we do decode output, we're going to pass it back through our tokenizer and we want to decode it this time. We're going to do token outputs 0. And we're going to go ahead and not skip special tokens. So we're going to go ahead and ask it to include the special tokens. That way we can see all of the output from the model, just in case we want to kind of investigate what it's doing under the hood. And finally, let's go ahead and print that out into our environment so we can actually see what's up. So let's go ahead and run the cell. So here you can see the decoded output from our model. You can see it gave a few reasons why Dr. Pepper is the best. And you can see we have one special token, which is the beginning of string token here. Basically just defining that this is the start of the input, so start generating after this. Now, usually there's also an end of string token down here, but we actually exceeded our max new token limit, so it just cut the generation off before it can actually output that final token. But usually there is one at the end of the input. So that is the basics of how to call the model. Let's actually go over how to actually have a conversation with the model. With all the instruction tune variations in the model, it has been trained to recognize a particular pattern and understand that it's not supposed to just continue the text, it's actually supposed to continue on in a conversational-like way. Like it's having a conversation with the user, not just trying to predict what should come next. So the structure of that prompt is as follows. So this is the structure of the conversation prompt for the Gemma type models. It goes in a turn-by-turn format like many language models actually do. And it starts off with specifying that this is the start of a conversation turn. And the immediately after that is going to define who is speaking this turn, in which case it's the user. So after we've specified who is talking this turn, we then have the text that they are actually saying in the conversation. And then we have another special token indicating that this is the end of the conversation turn. We then repeat the process with the next person in the conversation, in which case it's the model. So we're going to have another start of turn token. We're going to specify that the model is speaking during this turn of the conversation. Then the model is going to generate whatever it thinks the response should be for this part of the conversation. And then it's going to output an end of turn token. And then it's going to return it back to the user to have them input their turn. And so it goes back and forth like this until the conversation ends. So this is the general structure of the conversation prompt. So let's go ahead and see this actually in action. So we're going to define our prompt here. And since it's going to be multi-line, I'm just going to go ahead and use triple quotes, which is just a little bit easier way to do this. And we're going to start off with a beginning of string just so we have it included. We're going to start of turn. And we're going to start out with the user just like it's expecting. And let's imagine that we're asking it about what sort of snacks we should have at a pool party. All right, and so we do a start of turn, and we're going to specify that the model is going next. And we're actually going to leave the prompt here. So now we're leaving it ready for the model to actually pick up the prompt and provide its own input, which we can then read back to the user. So let's go ahead and turn this into tokens. Same way we did before, and let's pass those tokens into our model. And let's go ahead and say 1,000 new tokens. Let's give it plenty of room to wiggle and actually give us a really good response for this output. Now let's decode the output. And we're gonna go ahead and skip the special tokens for this particular experiment. And let's print out the output and see what we get. So let's go ahead and run this. Oh, it's input IDs. That's what I did wrong. Okay, double check your spellings. Make sure you're spelling everything correctly. And let's run it again. And there we go. So you can see that it did include our initial prompt here. So it has both turns of the conversation, but it did actually provide the model input for this conversation. And it actually produced quite a bit of text for our user to actually digest and include into their pool party. So that's the basics of how this conversation prompt actually works. Now let's talk a bit about how to just present the model output. Now it's entirely possible with some indexing to just get that output. So if we just want the new tokens, what we can say is new tokens is equal to token outputs 0. And what we're going to do is we're going to take our token inputs, just the IDs, and we're going to get its shape. And we're going to say basically anything after our token inputs ID, grab everything after that. So this is just some Python indexing because we know the length of what our input IDs were. We're basically just saying that everything after this length, go ahead and grab it and put it into new tokens. There's only one Z in tokenizer. I cannot spell today. My apologies. There we go. So this is how you would grab just the new tokens to present back to the user. It's pretty easy. You just need to do some indexing on the token inputs to get the new tokens. So while it's useful to understand how that conversation prompt is actually structured and to be able to create it yourself, there is an easier way to actually create that prompt using the tokenizer. So there is a function in the tokenizer called the apply chat template function, which can take in a list of conversation turns and actually produce this prompt for you, just in case you don't want to manage creating that prompt yourself. So in order to do that, first we have to define some conversation turns, and that's pretty easy. This is going to be a list of dictionary objects, and each dictionary is going to have two keys. One is going to be the role, basically who is speaking this turn, and each conversation needs to start with the user speaking, and then we're going to have the content, which is what they're actually saying this turn. So let's have the user ask, write a hello world program in Python, please. So we're asking for some code help here. So you can now use this list to kind of manage the chat. So whenever the model comes back with its own content, you would just create a new entry in this list for the model here as the role. And you would just keep adding to this list to create the next prompt in the conversation. So to actually convert this into a prompt, what we're going to do is we're going to do token inputs, because there is a way to go directly from this list directly into the token inputs from the tokenizer. We're going to say tokenizer.apply chat template. We're going to pass in the list of dictionary objects. We're going to ask it to go ahead and tokenize it. Although we can't have it return the text style of the prompt, this is just going to do both the converting it into a prompt and then tokenizing it into one steps, which is very convenient for us. And we're going to return tensors. Did I spell tensors? Yeah, that's it. As PyTorch tensors, and we're going to say add generation prompt is equal to true, just so that the model knows it needs to generate. And we're going to say to CUDA. All right, and this will convert it into the tokens that we need to feed it into our model, and it's all ready to go. And so now the rest of this is stuff we've already seen before. So we're going to say token outputs. Now, an important thing to note is that this doesn't return a dictionary object. This is going to return the tensor for the token inputs directly. So there's no need to index on this output to get the IDs. We just pass it in directly and it's good to go. All right, so let's go ahead and verify that this works. And there we go. So it gave a very brief response this time, basically just saying, hey, here's the Python code, no extra fluff to it. But that's kind of what we expected for this size of model. So as you can see, this is a very easy way to go ahead and create that chat prompt for us without having to actually manually create that string ourselves. And this is actually very convenient for us whenever we're making our applications. But it's still important to know what that prompt style is, just in case you need to fine tune it for your own cases later. So with the information you have already, you can go ahead and create a quick little chat application like I've done here on screen, and you can go ahead and start having conversations with your model. Now, there's a lot of places that we can take this, from quantization to make the model even smaller, to fine tuning, to going ahead and hosting this model somewhere on the internet where other people can interact with it. There's a lot more to explore, but this is the basics and how you get started with using these models from Hugging Face. So I hope this tutorial was helpful for you. If you want to see more of this type of content, let me know down in the comments below and what you'd like me to cover, and I will see you all in the next video.